Our third keynote speaker is Professor Lihi Zelnik Manor from the Technion. Professor Zelnik Manor is an associate professor in the Faculty of Electrical Engineering in the Technion. Between 2014 and 16, she was a visiting associate professor in Cornell Tech. Prior to that, she worked as a postdoctoral fellow in Caltech. She holds a PhD and MSc in computer science from the Weizmann Institute and a master's and a bachelor degree in mechanical engineering from the Technion. Professor Zelnik Manor will speak about image synthesis and the challenges it poses.
Oh, wow. Okay. Is this slide going to stay on? That's okay. So, avanti. Can you turn it off? I see like it flashes. I can't look at the audience. Thank you. Okay, now the spots are going to disappear. We just talked about eye issues. Now I have them as well. Okay, so thank you for inviting me. And we just heard two great talks. And one of the things that bothered me before I came here is what should I talk about? And this comes from the questions that I think has become important recently. What is our job in academia in computer vision? So for many years it was just us, just a bunch of geeks working on computer vision. But now look at you. There are like so many of you and you're all doing computer vision very successfully, and what is it that we should do? And what we decided in my lab is that our job is one is to, we need to produce engineers for you to hire and to start new companies and be very successful. The other task for us in our research is to look forward, to look ahead down the line and try to work on things that you won't be working on because they don't necessarily work today. Now some of the things I'll show you today do work today. These are just byproducts and it happened to be so, but our goal is actually further down the line. And what my lab is interested in is virtual worlds. So virtual, mixed, augmented, whatever reality you want to pick. We want to work on those environments, and we want the experience to be real. We want it to be immersive. We want the user to feel like he or she are there. And for that, we need, like, we as people, when we experience the world, we use all our senses. We are actually going to try and touch only two of our senses. The first one is the visual sense. We want the environments to look real. And if you look at this image, for example, I don't think it looks very real. So this is a result of a style transfer algorithm I'll talk about later on in the talk. It's a synthesized image. Now those virtual worlds, we are going to synthesize those worlds. So this is why I'm going to talk a lot about image synthesis today. We want it to look more like this. So this is one challenge I'm going to talk about. How do we generate images that look real? And the other challenge we're interested in, that I will just mention briefly in this talk, is does it feel real? And when I say feel, I really mean touching. Can we touch those virtual worlds, and will they feel like the real thing? And we need two solutions for that. We need to solve, there are many challenges that we need to solve for this to happen. My team is working just on two of them. The first one is hardware. We need good hardware, and this is like what you're seeing here. This is our state-of-the-art in my lab. Yeah, we're far behind. It's just actuators and wires and a little Arduino. So I know you had, so Chen said, I started as a mechanical engineer. This is my education. So I'm working together with Alon Wolf, who's a roboticist, on building devices for interacting with virtual worlds. So this is just this slide. I won't talk about the hardware today, but I will mention a little bit at the end. Our job as computer vision people, in order to provide those devices with the right information, we need to be able to go from an image to a surface. And what you're seeing here at the top are two images, and at the bottom examples of our results of reproducing the surface normals. And we're using a common color scheme to show the normals, but I think you can get the sense of really fine texture that we can reconstruct. Or here's another example. We just have those images at the top, and we can reconstruct the fine details of the 3D texture and then we can display them from all kinds of viewpoints and different lightings, etc. But let's start with the first challenge that I talked about, not touching things, but rather looking at things when we want to generate images that look real. And as a case study, I chose the problem of style transfer. Now, this is a cute problem where you're giving an input image, in this case, this cute, funny dog at the top left, and you're given a target image, in this case, this yellow cat, and you want to generate an image, a hybrid image. Essentially, this image typically should have the spatial layout of the dog and the style features, the appearance of the cat. And you see here the result that we get. You can tune how doggish or how cattish this will look. But this is just the parameters we chose, and this is the result. Sorry. A good way for doing this is to train a convolutional neural network for doing the task. Now, this setup where you're given an input image and a target image, and you want to generate an output image, is not just relevant in style transfer. We have the same setup in many, many other image generation tasks. So just, for example, in single image super resolution, the input is a low resolution image, the target is a high resolution image, and we want to train a network to go from low resolution to high resolution. And you can think of many other applications, like in painting, denoising, animation. In many, many tasks, you train a network to generate an image. Okay, so let's go back to our case study, to the style transfer. And how do you train the network? So you can work on the architecture, and people are doing that. But regardless of what your architecture is, a key factor is how do you measure that your output is indeed what you're looking for. And this boils down to a loss function, and the loss function compares the image that you generated to the input dog and the target cat. Now, what loss function do we have available? So currently we can categorize the loss functions into two groups. One of them are pixel-to-pixel loss functions that compare pixels at corresponding locations. So this is L1 norm or L2 norm, or even the perceptual loss functions which you're familiar with, they take from the image the deep features and compare the deep features. But the comparison is done at corresponding spatial locations. And now, before when Lior gave his talk, Michal asked him, what happens if the zebra is at the top left corner of the image and the horse is at the bottom right corner of the image? How do you compare them? And if you use one of those losses, you're doomed. In this case, you can use these losses to compare the output dog to the input dog, but you cannot use it to compare to the cat in order to get the cat's style. Another family of loss functions are more global, and essentially there is one that has become popular. It's called the gram loss, and the gram loss collects statistics over the entire image. And this is why and this is what is being used in style transfer or texture synthesis, and people are actually using it also for other image generation tasks to capture the style of the target. But it collects statistics over the entire image. So for example, the actual results that you get for this pair of input images is what you're seeing here at the bottom left. And you see the dog got those yellow and white blotches of color, but in the wrong locations. This is because, again, this is a loss that just aggregates the texture statistics over the entire image. So this is not good enough. And again, just to show you another example, this is the classic example of style transfer. You take a picture and a Van Gogh painting, and you can generate a Van Gogh-like version of this picture, which is cool. But if you look at all those yellow stars, they're just all over the picture. In the buildings, in the water, on the trees, there's no semantic meaning. It's wrong semantics. So maybe it's beautiful and great, but if you do want to maintain semantics, it doesn't work. So what we want is a way to measure similarity between images, but we want a semantic similarity. We want the eyes to be compared to the eyes, the nose to the nose, the forehead to the forehead, etc. So how do you do that? So luckily we came up with a solution. So this is the problem layout. And what we do is we took a statistical approach. So we take the target image, this cat. Okay. We took the target image, we took the cat, and we pass the cat through some feature extractor. This could be a deep network like VGG, it could be patches, it could be whatever you choose, but we go from image to a collection of high-dimensional points, a set of features. We do the same to the image we generate. Okay, see, animations don't work. Okay, but now we have, rather than two images, we have two sets, two distributions of points, two distributions of features, and we compare those distributions. So we find matches between the distributions, and we propose a loss function that measures the similarity between the distributions. Now, I'm not going to go into equations, but this is the important thing. This is the take-home message from this entire talk. We want to compare distributions of features. And the important thing you want from your measure is for it to be able to distinguish between similar distributions and different distributions. And this way, when you train your network, if you start from an image that doesn't look good or it's not similar to the target, you will modify its features, you'll modify the patches, its deep features, whatever features you chose, you will modify them slowly and slowly until you get something that matches your target. So let's go to style transfer, and just to show you what we can get with this approach of comparing the feature distribution statistically. We took style transfer, we took one of the state-of-the-art solutions by Gatis, it's called neural style. We took their architecture and we just replaced their loss function with ours. And this is what we get. We can take Mr. Bin and Hillary and get Mr. Binary. And you can see he got her lips, he got her eyes, even some highlights in his eyebrows. Cool. Obama and Hillary. Totally cool, I think. I love this one. We can make Obama a bit surprised, like Mr. Bin. A cool Barack De Niro. I love this one, Hillary and Obama. You can see she even got, I don't know if you can see, maybe you can. She even got, he has this little mole next to his nose, and she even got that. She got his eyebrows, his eyes, some of the skin tone. And again, we can tune how much Hillary and how much Obama this will be. This is just what we selected. I don't have this, but you'll get him with some of her features. So like, let me go back. So this is Obama and Hillary reversed. So it's more Obama with her lips and eyes. But you can tune the parameters. We tuned them. We just selected a set of parameters, and all the results here have the same set of parameters, but you can play how much it will be more like him or her. So this is cool, but I wanted to generate real results, and maybe you say, okay, these have artifacts. So first I'll start by saying, okay, I told you, we're not necessarily trying to work on problems that can be perfectly solved today. We're happy with working on problems that will be solved a while from now. But just to convince you that we're doing okay, that we made progress, because style transfer is so subjective, I'll show you some results from our competitors. So you can see again, we took not people, but two dogs, and our results are on the top, and you can see that we replaced the dog's eyes, we replaced its nose. There are really semantic matches across the images. And at the bottom, you see competing results. Bottom right, the results by Gatis. So this is, if you compare Gatis to our result, exact same architecture, we just replaced the loss function from pixel to statistical comparison. And the other result, the CNN MRF, this is actually an approach that had the same idea as ours. They said images should be compared semantically, and they compared deep features, but their framework suffers from a lot of artifacts. As you see, you get really, really weird dogs. So does it look real? Our result does go in the right direction of improving over previous work. Another example, really funny. And this sad cat becomes also yellowish. I like them. Okay, and a nice outcome of this approach of compare images semantically and statistically, we can use it also for other tasks, and I'm glad that Lior talked about domain transfer, because now I can speed up what I say. So we try to use this for gender change, and as Lior told you, this problem is difficult because you don't have training pairs. So if you want to make men, for example, want to to take male images and make them more feminine, we don't have the matching feminine version for each male picture in our data set. And we will never have that. Not everybody is going to go through this whole process of gender change, and so we won't have the data. So what is the best we can do? So the current solution that is popular in the community is to use cyclic approaches that says, okay, let's take a male image, make it into a female, go back into male, and we should end up at the same point. And there's discogun and cyclegun, which are great, but they're difficult to tune. Now, Lior showed you one way to actually do domain transfer without a cycle, and our approach also does it without a cycle. We take random pairs of male and female. So we take a guy's picture, we pass it through the network, we get something, and we can compare it to any female picture because we don't care that they're not aligned. We're just comparing the feature distributions, the statistics within the image. And so these are the guys, and this is what they look like when we make them more feminine. Look at their eyebrows. They went to the beautician, right? So they're now nicely shaped. Lips are more pronounced, even some eye makeup. We can also go in the other direction. So we can make women more masculine and bushy eyebrows, square features. And again, do you think these results are good? So the best we can do, we can compare to previous work. So the top here, the top row is the source. In the middle, you see result from cyclegun. At the bottom is our result. I think that we're doing a better job. And you can see, by the way, one of the things you can see here, one of the problems of the cyclic approach is that one direction works better than the other. So I think I don't know if male to female works that well. Female to male maybe works better for cyclegun. For us, it's the same. It's just a single feed-forward network with no gun. For comparison, we just compare to cyclegun. We had their data. So Lior asked, why do I compare to cyclegun and not discogun? We just, I don't know, cyclegun is popular, and we compare to cyclegun. We can compare to discogun. But regardless, we're just using a single feed-forward network and not a cycle. So we're happy with these results. But do the images that we produce look real? So let's go back to style transfer. And what you see here is the result from Gatis. Content image is on the top left, the target style is on the top right, and the result you see here in large. And this really doesn't look like a photograph. It doesn't look real. So one thing we tried to do, and this way something we published at BMVC, we tried to see why doesn't it look real? And you can actually manipulate the gradients of the image to go from here to here. It's a simple gradient manipulation, and the key to this is that if you take a real image and one generated by one of those networks, what you see is, and you look at the distribution of gradients. So in yellow, you see the distribution of gradients of a real image. In red, it's the distribution of gradients of a fake image. And you see they're different. Now, this is really, really, really old news. So already in the 90s, Roderman told us that natural images should have a power spectrum that looks like a sparse distribution. This is the original image from his paper. I put there as an inset something that looks a bit clearer. And then we heard from Michal Irani's group many, many times that there's recurrence of patches within an image, and this is something that we should use, and images should exhibit this behavior. And from Yair Weiss and Anat Levin, we heard that image priors on the likelihood of patches are really, really effective in any restoration task. So this has been known for years in the 90s and early 2000s, and we're not using that. But if you think about what I tried to propose here, I said, look, when you're trying to train your network, don't just synthesize an image and compare it pixel by pixel. Compare the statistics, compare the distributions of features, the distributions of patches. So essentially what we're doing in this approach, we're generating images with more natural statistics. We're maintaining the internal statistics of the image. And to convince you that indeed this is what we're doing, let's put aside style transfer, which is hard to measure. It's nice results, but not quantifiable in an easy way. We went to single image super resolution. You get an input image, low resolution, you want to generate a high resolution target image, and here you can measure your success. So you can generate ground truth data and compare results with the ground truth. And what we used here, again, we just used our statistical loss function, so when we train our network, we compare the statistics of the images that we generate to those of the target, of the ground truth. And we picked a recent architecture called SRGAN, and we just added to it our loss. And just, this is a typical input, and this would be a typical result. And you can see that we hallucinate the textures, the edges. Again, input and a result. And just to convince you that indeed we were maintaining the internal statistics, what you're seeing here is a projection of the image patches. Every point here is a projection of a 5x5 patch. In magenta, the target image. This is the goal, the high resolution ground truth. In green, the image we generated. And it becomes dark when they overlap. Now this is when we begin the training. Now as the training proceeds, the network becomes better and better, and the images that we generate have statistics more similar to the target, and you see that the distribution is more similar, and everything is dark, which means there's an overlap between the target and the generated image. And just another projection to make sure, to kind of convince you that this is just not just a cherry-picked example. And you can actually also, but if you just look at the loss function, so obviously we minimize our loss function. Our loss function measures the similarity between distributions of patches between the two images, the ground truth and the one we generated. So this obviously is minimized during the training. But you could also take other statistical measures for comparing distributions, like Kolbach-Leibler, and you'll see that they are minimized along the way. Sure. So again, our results. So this is an image. It is enlarged with bicubic. This is just for reference. 2009, we were here. This is a work by Daniel Glasner and Michal Irani from ICC 2009, based on patch recurrence, internal statistics, which is a huge improvement. SRGAN, 2007, last CVPR, looks even better. This is our result. And I just flip back and forth, very, very mild differences. Hard to see, hard to notice. And this is the ground truth. But if you look closer into the differences between what we give you over SRGAN, you will see that they hallucinate textures. So if you use evaluation measures, how realistic are their results, you'll get good results. But they hallucinate them. They produce too much texture, and sometimes in the wrong locations. They just generate texture, so the measures tell them, the quantitative measures tell them it's a good result. And you can see here the ground truth on the right, I think maybe the best, I don't know, on the screen, maybe on the ear, it's easier to see the ground truth, what we get and what SRGAN gives you, which is, it has redundant high frequencies. And going just related to Ruderman's paper that said a natural image should have a certain power spectrum. So these are the power spectrum of images generated or super resolved by our approach or other approaches. And you can see that the recent approaches that try to get perceptually good super resolved images, they get power spectrums that are similar to those of natural images. So GAN does a lot of the work, and we add an extra thing there. Even though Lior said the GANs do most, yeah, here GANs do most of the work, we just improve a little bit. I'll skip the quantitative. But if you go to other problems, and again, I told you we don't want just to look at images, we also want to touch them. And if you want to go from an image to the normals, then GANs are not as successful, mostly because you don't have that strong, that well-tuned architectures for features. But if you think of surfaces, they also have natural statistics similar to those of images, just because the surfaces we're seeing are man-made, the images we're seeing are of man-made environments, so there's a correlation there. And if you use this idea that when we take an image and we try to reconstruct its fine 3D surface, the corresponding 3D surface, that surface should maintain the internal statistics of natural surfaces in this world. But these are our results, and you can see here again, the ground truth on the right. So we were given just a single image, and we generated a 3D surface. The ground truth is on the right, our result in the middle, and on the left, it was it's using the same architecture, but with a traditional loss function. And another example, and you can see that they don't get the high frequencies. And I believe using GANs for this will be more challenging than for images. So I'll conclude. I'll just say, it works here. Okay, it doesn't work on my screen. So just a last cute example of single image animation. So we have this animation of Ray Kurzweil, and on the right a single image of Zuckerberg, and we're animating according to Ray Kurzweil, and we can compare the images because we're just comparing the statistics. And a cute citation from Mark Twain, facts are stubborn things, but statistics are pliable. So we recommend generating images that maintain internal statistics or natural internal statistics. There are things that we've known in computer vision for many years now, and we should find the ways to incorporate them into those new tools and architectures. So I'll conclude. Thank you.
Hi, hello. Do you use an FFT algorithm in any of your image generation tools?
So do we use
an FFT, a fast Fourier transform?
No.
Thank you.
These are all CNNs.
Hi, I just wanted to know if you're using only high-level layers for the statistical comparison of the features, or all the...
So it depends on the application. Sometimes we use the high-level features, sometimes we use also coarse level. You need to think of what it is that you want to get, and then you can tune for more spatial layout or more...
For the style transfer specifically?
I think so in style transfer we compare to two images. We compare to the input, to the content image, to the style image. For the style we use higher layers, and for the content lower layers.
Thank you.
Sure. I have a question here.
Yeah, hi.
Okay.
How is your loss actually different from using a GAN? Because basically what we're trying to do is saying, okay, the distributions are very similar, so in a GAN architecture I would have the discriminator.
So GANs, essentially what they try to do is say, let's look at the distribution of images, and let's generate an image that is somewhere in this space of images. And we're just taking one step. I said, okay, let's look at the components of this image, the specific image we're generating, and make sure that the distribution of features within this image matches not just a natural distribution, but the one of the target image that we're training with. So our networks, they add another, it's another step. You can think of it as it's trying to do this, it's the same goal as GAN, it's the same goal, but it's a simple implementation. It's just a loss function. You can plug it into any architecture. GANs are a little difficult to train, so this is just a very, very simple solution. Replace your loss. And I didn't emphasize it, but we use here like all kinds of applications. For each one, we chose an architecture, and we just plugged in our loss, and that's it, and you get what you want. So it's cool. Except for the super resolution, we did use GANs, but all the other results, we have the gender change, no GANs. No GANs.
So I think we will try to keep up with the schedule, so I hope you can ask Lee later.
I'm around,
Okay.
so.
Thanks, Lee, again.
Well, thank you, everyone.